Hi all. So we'll be continuing with our class on AET. So we have been looking at module number 3. So in today's lecture we are going to look at oblique incidence with two types of polarizations, that is parallel and perpendicular. So again we will be continuing with our oblique incidence. Now just to recap, so let's say assume that you have two different media along this boundary. The first medium, let's say it has medium 1 has permittivity epsilon 1, permeability mu 1, intrinsic impedance eta 1, etc. And there is another medium 2, which has permittivity epsilon 1, epsilon 2, permeability mu 2, intrinsic impedance eta 2, etc., etc. Now, when wave traveling in an arbitrary direction instead on a medium, it gets reflected and it gets transmitted. Okay. So, let us say that this is your z axis. Okay. So, the plane or in which the wave is incident or the boundary in which the wave is incident is at x z equal to 0. So, when the wave gets incident on this plane, on this boundary like this, some part of the wave will get transmitted, some part of the wave will get reflected. Okay. So, to draw it more accurately, the angle of reflection will be equal to the angle of incidence. So, where this is your theta I, this is theta r, and this is theta t. Okay. So, we know that there is something called as a wave vector associated with a wave propagating in arbitrary direction, which we denote as k. It is called as propagation vector or wave vector, wave number vector. So, this is for incident wave, this is for transmitted wave, and this is for reflected wave. Now, all the characteristics of the wave will be same. That means there will be electric field, there will be magnetic field, and both will be perpendicular to each other, and both will be perpendicular to the direction of propagation. So, here the direction of propagation is indicated by the k vector. Okay. And we have seen that we have derived the expression of Snell's law, which states that the refractive index n1 into the sine of angle of incident is equal to the refractive index of second medium into sine of angle of transmission. So, this we have derived in the last class, where n1 is the refractive index of medium 1 and n2 is the refractive index of medium 2. And we also seen that we can represent n1 as the product of the velocity of light in the square root of mu 1 epsilon 1, and n2 is equal to the product of velocity of light into square root of mu 2 epsilon 2. Okay. Also, we have seen that there is something called as a plane of incidence. Okay. So, basically the wave is traveling is incident on the boundary in this plane. So, the reflected wave, incident wave, the transmitted wave are all in this plane. And if you give, let us say, this as x axis, your y axis will be towards the plane of paper or towards u, which will be y. So, the plane of incidence is in x z plane. So, that is the plane in which the wave is propagating. Okay. Now, this is regarding the recap. Now, let us define some terms. We told that there will be electric field and magnetic field for the wave, for incident, reflected and transmitted. Now, what will be the direction of electric and magnetic fields? We can choose any arbitrary direction. We are going to choose two different cases. First case is the case in which your electric field is in the plane of incidence. That is called as parallel polarization. Means the electric field, whether it is incident, reflected or transmitted, the electric field is in the plane of incidence. So, we give the name as parallel polarization. Do not confuse this polarization with our polarization that we have seen, that is circular everything. So, this is a polarization in which we are saying that the electric field is in the plane of incidence. So, how does the diagram now looks like? So, let us draw the diagram again. So, this is your x axis, this is your z axis, the wave gets incident, it will get reflected, it will also get transmitted. Okay. And let us say this is theta I, angle of incidence, angle of reflection, angle of transmission. The wave vector, let us say this is in this direction, which is k I, this is k T, this is k R. Now, we are saying that the electric field is in the same plane like this. So, this is E I, okay, and you will have E R also in the same plane and E T also in the same plane. So, you see E R, E I, E T is in the same plane as that of the plane of incidence or the plane in which the wave is propagating. Okay. And your H is perpendicular to the plane of propagation. So, this is H R, this is H I, and this is H T. You see, the H vectors are perpendicular to the plane of incidence. It is either towards you or into the plane of paper. H I and H T is towards you and H R is into the plane of paper. But the electric field is in the same plane as that of the paper or the plane of in which the wave is propagating. This is called as parallel polarization. Okay. Now, let us try to see or let us try to find out what is the relationship between the reflected, transmitted and incident waves. Can we quantify them? So, that is what we are going to look at. Okay. Now, this needs some amount of vector analysis. Okay. Now, let us start with medium 1. So, I am saying I am not taking e raised to j omega t in our equation, as we have already told earlier. I will be taking only those terms which are relevant. Okay. So, the electric field incident without e raised to j omega t consists of two components. Why? Because you see this is oblique, you mean it is in a slanted way. So, you need to find the components of EI along the direction of axis. For example, in this case you can resolve the components into two. For example, I will draw this separately. So, E is something like this, EI. So, I can draw as there is one component like this, there is another component like this. Okay. The component which is towards left is parallel to the z axis. So, this component is parallel to z axis and this component is parallel to x axis, which means I have resolved the electric field into two components along z axis and along x axis. Now, what is the value of those components? For that, you need to find the angle. You see, this angle is theta I. You can do some mathematical calculations. This is like something like this. So, this is theta I, means this is also theta I. So, that is what I have drawn here. So, the component along x axis I can write as, let us say I write as E I S x is E I 0, let us say it is the magnitude of E I cos theta I. Sorry. So, there is a small correction. So, this is not theta I, because you see these are the perpendiculars, and so the value of this will be theta I. That means you have theta I here. So, the component along x is towards up, that is this one is towards up, which is positive x, and component along z is towards left, which is minus z. Okay. And the component along x I can write as, this is the magnitude E I 0 cos theta I A x cap. Similarly, the component along z is equal to E I 0, there is a minus sin theta I A z cap. Why there is minus? Because it is in the direction opposite to that of positive of z. Okay. So, these are the two components. So, I can write now EIS as EI0, I am just combining both, into cos theta I x cap minus sin theta I a z cap into e raised to j k I dot r. This we have seen in the last class, that when you have a wave traveling in an arbitrary direction, you have the dot product of position vector and the wave or propagation vector, where r is x ax cap plus y ay cap plus z az cap. Now, we are assuming a lossless media. So, your Ki will have the magnitude of beta 1 because it is of the medium 1. So, the phase constant of the first medium, we are assuming it as beta 1. Okay. Now, you see Ki is not in parallel with any of the axes. Ki is in an arbitrary direction with x axis and z axis. So, just like we have did for Ei, we need to do for Ki to resolve it to find the components along or parallel to x and z axis. So, let us do that. So, your Ki direction is like this. That means, I can resolve it into two components like this and like this. So, this is Ki. Okay. So, the two components are, one is along positive z and other is along positive x. So, this is along positive z and this is along positive x, because your x direction is like this and z direction is like this. What is the angle? You see, the angle here will be theta I, that you can see directly from this figure. So, this is this one. So, if you resolve this, this angle will be same as this angle, that is the basic geometry. Okay. So, I can write now Ki x, the component along x, as sin theta I ax cap. Okay. So, this in the triangle, in the vector triangle, the side which is opposite to the angle will be of sine and side which is near to the angle will be of cos. Okay. Similarly, Kiz is equal to cos theta I az cap. Okay. Where this is Kix, this is Kiz. Okay. Fine. So, now I can do, and also we know that the magnitude is beta 1. So, now I can write Ki as beta 1 into sin theta I x cap plus cos theta I az cap. If I do the dot product Ki dot r, you will get. So, basically you are giving the dot product of Ki and r. So, you will get beta 1 into x sin theta I plus z cos theta I. You see, this is not a vector, but a scalar. So, let us substitute this in here. So, substituting in EIS, you will get EIS is equal to EI0 into cos theta I x cap minus sin theta I a z cap multiplied by e raised to j into beta 1 x sin theta I plus z cos theta I. So, this is the expression for EIS without e raised to j omega t in for the incident wave. So, what will be the expression for HIS? We have already seen that HIS will be EIS divided by eta 1 because it is in the first medium. Now, the good thing about HI is it is perpendicular to the plane of the paper, which is towards you, and it is not at any angle. Okay. So, HIS is directly coming out, it is not at any angle, or in another way you can say that it is along the y direction. You see the y direction and HI directions are now parallel because HI is towards you, y is also towards you, which means I can write HIS as, so I do not want to resolve HIS into components because it is already parallel to the y axis. So, I can write HIS as EIS or the magnitude of EIS, which is EI0 by eta 1 e raised to, I am sorry, there is, I think there is a minus sign, I forgot, there is a minus here, e raised to minus j beta 1 x sin theta I plus z cos theta I. Now, you see this part will remain the same because it is same incident wave. So, this will change only if the wave is of different type, incident or reflected. Since both EIS and HIS are for the same incident wave, this part will remain the same. Only change will happen in this part. So, since E is some angle with respect to the x and z axis, you need to resolve the components sin theta and cos theta. Since H is parallel to y axis, you do not want to resolve into any components, and you can directly write this a y cap. Fine. So, this is regarding the in medium 1 the incident wave. Now, let us look at reflected wave. In a similar way, just that like we have did for incident wave, we can do it for reflected wave. So, in the reflected wave case, your ER is in this direction. Okay. So, I can resolve this into two parallel directions, resolve in two perpendicular directions, one parallel to x and one parallel to z. So, this is ERX, which is parallel to x, and this is ERZ, which is parallel to z. Okay. And the angle, if you look at the angle, this is theta r, so this is also theta r. So, which means this is theta r. Sorry. So, this is theta r. So, this is 90 minus theta r. So, sorry, this is theta r, this is 90 minus theta r, which is this is theta r. So, I can write this as theta r. So, my ER ERX is equal to So, theta r is adjacent to ERX, which means the component of ERX is sin theta r, or I need to write with the magnitude also. So, EI0 sin theta r x cap, ERZ is equal to EI0, sorry again, this is cos theta r x cap, this is sin theta r AZ cap. Also, if I resolved the propagation, so propagation is in this direction, so I can resolve into two components parallel to x and z. So, this is kr, okay. So, there are two components like this. This will be theta r. So, I can write krx is equal to, so x is in this direction which is parallel to this, which is opposite side of theta r. So, x will have a cos theta r, sorry, sin theta r component. So, this will be, sorry, sin theta r x cap. Now, krz is equal to, you see z is in the opposite direction. See, this is negative z because your z is in this direction. So, you will have minus, and z is along or near to theta r. So, I can say that is minus cos theta r AZ cap. So, now I can write my complete equation as ERS is equal to EI0 multiplied by the sum of these two terms. This cos theta r x cap plus sin theta r AZ cap multiplied by e raised to minus j. Just like we have ki dot ar, we have kr dot r, where kr dot r is equal to, we know already r, this a x cap plus y cap plus z AZ cap. So, I can write kr dot r is equal to kr, which is the sum of these two terms. So, I can write sin theta r ax cap minus cos theta r AZ cap dot x ax cap plus y ay cap plus z AZ cap. So, this is equal to x sin theta r minus z cos theta r. So, I can write ERS is equal to EI0 by, sorry, EI0 multiplied by cos theta r ax cap plus sin theta r AZ cap into e raised to minus j beta 1, because the magnitude is beta 1. So, this is multiplied by beta 1 into x sin theta r minus z cos theta r. Similarly, HRS is equal to, you see HRS is towards the plane of paper. This indicates that it is going into the plane of paper, which means it is in the opposite direction of y, but it is parallel to y, because of which we don't want to resolve into components. So I can directly write HRS is equal to minus ER0 by eta 1. So I think I need to change this into ER, because the magnitude of reflected and incident wave can be different. So I think I will also change it here. ER0 by eta 1 into e raised to minus j beta 1 into x sin theta r minus z cos theta r. This is a y cap, because it is in the opposite direction of y, but it is parallel to y. So that we have found for the reflected wave. Now let us look at medium number 2, transmitted wave. So in medium 2, we will follow the same procedure. So your ET is in this direction. So I can resolve into two components. So ET is like this. One is along Z, which is this ETZ, and one is along X, which is ETX. Now again, the angle is, this is theta t. So the value of ETX is, it is adjacent to theta t, so it is cos theta t AX cap. Since it is in the parallel direction of x, that means it is positive. So this is x, ETX also in this direction, so it is positive, and it will be multiplied with the magnitude ET0. Similarly, ETZ is equal to ET0. Now the value of it is in the opposite direction. So Z is in this direction, ETZ is in this direction. So I can write this as minus sine, because it is in the opposite side of the angle, sine theta t AZ cap. Now again we resolve KT. So KT is something like this. So I can put it as two perpendicular vectors. One is parallel to Z, one is parallel to X. So this is KT. The angle, it is evident from the figure that this is theta t, right. So this is KT, this is theta t, KT, this is theta t. Okay. And you will have KTZ and KTX. Now KTZ is in near to the angle. So I can write KTZ is equal to cos theta t AZ cap. It is in same direction of Z. KTX is also in the same direction of X, but it's in the opposite side of angle. So this is sin theta t AX cap. So now let's bring them together. So our ETS is equal to ET0 multiplied by the sum of these two terms. cos theta t a x cap minus sin theta t a z cap multiplied by e raised to minus j. Now, there is kt dot r, which from the above two derivations now you will be understanding it is beta 2 because of it is in the second medium into x multiplied by cos theta t and y z multiplied by sin theta t. So, this is x cos theta t plus y sin theta t. So, not y, it should be z. Now, if you look at HTS, you see HT is towards you, which is in the same direction as that of y. So, HT is like this, y is also like this. So, those are in parallel directions, which means I do not want to resolve HT. I can directly write this as ET0 by, this is intrinsic impedance of second medium eta 2 e raised to minus j beta 2 into x cos theta t plus z sin theta t. Okay. So, now we have found out all the expressions of electric and magnetic fields in both the mediums. Okay. We now will apply the boundary conditions. So, as per the boundary conditions, the tangential components of electric and magnetic fields are continuous. So, applying boundary conditions. First one, E tangential in medium 1 should be E tangential in medium 2. Second one, H tangential in medium 1 should be equal to H tangential in medium 2. So, let us find out the tangential components. So, in medium 1, you see that the tangential component is the one whose component is along x axis, because this component is perpendicular to the boundary, while this component is parallel to the boundary. So, in medium 1 and 2, you find out all the components which are along x, that is your tangential component, because you see if it is a z component, it is perpendicular to the boundary. If it is only x component, it is parallel to the boundary, or in the case of H, it is always parallel because it is along y. So, y means it is grazing. So, x is something like this, okay. The boundary is something like this, and the y is parallel to that. Y is parallel to the boundary. So, in medium 1, the tangential component is the component which has x as the unit vector, which is for the incident wave it is this one, for the reflected wave which is this one, and for the transmitted wave which is this one. So, the total tangential component in medium 1 is E r x plus Eix. The tangential component or the component of x along of the reflected wave and the tangential component or the component of x of the incident wave, where Erx is Er0 multiplied by cos theta Ax cap into whatever e raised to j this term is. So, I can write this as Er0 cos theta I into e raised to minus j beta 1 x sin theta r minus z cos theta r. Okay. Similarly, Eix is equal to Ei0 cos theta I Ax cap, which means this is Ei0 cos theta I into Ax cap, which is because of x, multiplied by this term. Sorry, that is for reflected, this is for our incident. Okay. The sum of this is the total tangential component. Now, you see the wave is incident on z equal to 0. Okay. So, this plane, this boundary is actually at z equal to 0. So, you can substitute z equal to 0 implies Erx plus Eix is equal to Ei0 plus Er0 into cos theta I e raised to minus j beta 1 x sin theta I plus x sin, or let me write it properly, Er0 cos theta I plus Ei0 cos theta I e raised to minus j beta 1 x sin theta r plus Ei0 cos theta I e raised to minus j beta 1 x sin theta I. Okay. Similarly, for medium 2, you have the transmitted wave and the component of along parallel to boundary is Etx is equal to Et0 cos theta t e raised to minus j beta 2 x cos theta t multiplied by e raised to minus j beta 2 x cos theta t plus z sin theta t. Now, z equal to 0 because you are evaluating at the boundary. So, this minus j beta 2 x cos theta t. Okay. Now, by Snell's law, you know that theta r is equal to theta I, implies ERX plus EIX is equal to ER0 plus EI0 into cos theta I e raised to minus j beta 1 x sin theta I. And ETX is equal to ET0 cos theta t into e raised to j beta 2 x cos theta t. Now, at the boundary, the magnitude of the tangential components are same. Okay. Actually, I should have written this as magnitude. Now, when you take the magnitude, you see the e raised to j theta term will vanish. So, this term, when you take the magnitude, this will be equal to 1, this will also be equal to 1. So, I can write by applying the boundary conditions, ER0 plus EI0 into cos theta I is equal to ET0 cos theta t. So, this is, let us say, equation number 1. So, here let me be more clear. Basically, the magnitude of the tangential components are same in either side of the boundary. When you take the magnitude of the tangential component of medium 1, e raised to j theta term will vanish, because you see that when you take the magnitude of this term, then the value of the magnitude of this is equal to 1. So, that will vanish. So, when you take the magnitude of this term, the magnitude of this is equal to 1. So, that will also vanish, because this is the only complex part and this is real. So, this part will have magnitude 1. E raised to j theta, the magnitude of e raised to j theta is equal to 1. Okay. So, we will get something like this. In a similar way, if you apply the boundary conditions of magnetic field, you will get the equation something like this: 1 by eta 1 E I 0 minus E R 0 is equal to 1 by eta 2 E T 0. This is equation number 2. Now, I would suggest that you do this as a homework, that is, derive this. You can follow the same procedure as that of electric field. You find the parallel components or tangential components, which in this case will be the same as that of H. So, whatever H is there, it is tangential. This is tangential, this is tangential, and this is tangential. Now, you are evaluating at z equal to 0, you put z equal to 0. So, this will vanish and this will vanish and this will also vanish. Now, theta I is equal to theta r, okay, because of the Snell's law, and you can substitute it and you will get this equation. Now, you get two equations, equation 1 and equation 2. Now, we are going to find out what is the relationship between ER0, EI0 and ET0. Remember, ER0, EI0, ET0 are the magnitude of electric field of reflected, incident and transmitted waves. Okay. Fine. So, let us do some manipulations to evaluate this. So, let us do one thing. In equation 2, I can write this as EI0 minus ER0 is equal to eta 1 by eta 2 ET0. This is equation number 3. And equation 1 I can write as EI0 plus ER0 is equal to, I am just taking this cos theta I to the left hand side, right hand side. So it is Et0 into cos theta t by cos theta I. Let's say this is equation number 4. Let's add 3 and 4. So you get 2 ei0 is equal to Et0 multiplied by eta 1 by eta 2 plus cos theta t by cos theta I. Okay, so let's do some more manipulations. This is Et0 into eta 1 cos theta I plus eta 2 cos theta t by eta 2 cos theta I. So I can bring the 2 down. So ei0 is equal to Et0 into eta 1 cos theta I plus eta 2 cos theta t divided by 2 eta 2 cos theta I. So if I take the ratio of Et0 by ei0, this is equal to 2 eta 2 cos theta I divided by eta 1 cos theta I plus eta 2 cos theta t. This is called as the reflection coefficient of parallel polarization. You see, you can find out how much amount of incident wave is reflected, transmitted. So this is the transmission coefficient of the parallel polarization. This is the transmission coefficient of parallel polarization. Similarly, you can manipulate equations 1, 2, 3 and 4 to find out the relationship between ei0 and er0. Okay. So maybe I'll also derive that. From 1, Et0 is equal to er0 plus ei0 into cos theta I by cos theta t. Okay. And from 2, so this is, let us say, the equation number 5. Et0 is equal to eta 2 by eta 1 into ei0 minus er0. So this is equation number 6. So equation number 5 and 6 are equal because at both left hand side it is Et0. So I can just write er0 plus ei0 into cos theta I by cos theta t is equal to eta 2 by eta 1 ei0 minus er0. Now let us take all the er0 terms common and ei0 terms common. So just let us bring ei0 to the left hand side. So let me expand this. er0 cos theta I by cos theta t plus ei0 cos theta I by cos theta t is equal to eta 2 by eta 1 ei0 minus eta 2 by eta 1 er0. So let us bring ei0 to the left hand side and er0 to the right hand side. So we will get ei0 into eta 2 by eta 1, or I would say cos theta I by cos theta t minus eta 2 by eta 1 is equal to ER0 into minus eta 2 by eta 1 minus cos theta I by cos theta t. So, I can write this as EI0 into eta 1 cos theta I minus eta 2 cos theta t by eta 1 cos theta t is equal to ER0 into minus eta 2 cos theta t minus eta 1 cos theta I divided by eta 1 cos theta t. Now, the denominator is same in both left hand side and right hand side to get cancelled. So, you can write ER0 by EI0 is equal to, there is a, you can take a minus sign common on the right hand side, so that will become plus. So, when the minus sign comes here, it will be eta 2 cos theta t minus eta 1 cos theta I whole divided by eta 2 cos theta t plus eta 1 cos theta I, and this is called as the reflection coefficient of parallel polarization, where you can relate how much amount of incident electric field is reflected back. So, this is the reflection coefficient of parallel polarization. Now, see, there is a relationship between reflection and transmission coefficient, which is 1 by 1 plus tau parallel is equal to small tau parallel into cos theta I theta t by cos theta I. This you can try as homework to find this relation. So, there is one more important concept that we can see. So, if you look at the numerator of this reflection coefficient, you see that if the eta 2 cos theta t is equal to eta 1 cos theta I, then your reflection coefficient will be 0, or whatever wave is incident, it will be completely transmitted. So, for eta 2 cos theta t is equal to eta 1 cos theta I implies tau parallel is equal to 0, implies all the incident wave is transmitted, or there is no reflection. Why? Because this is actually ER0 by EI0, implies ER0 is equal to 0. So, the angle, so basically what is it, what is the one which will decide whether there will be a complete transmission? That is basically the incident angle. Okay. So, the angle at which there is complete transmission is called as Brewster's angle. The angle of incidence at which there is no reflection is called as Brewster's angle. That is, at theta I is equal to theta b parallel, you will have complete transmission. So we can find the angle value. So we know that at Brewster's angle, eta 2 cos theta t is equal to eta 1 cos theta Brewster. So let's square both the sides. So we'll have eta 2 square cos square theta t is equal to eta 1 square cos square theta b. Now cos square theta t is 1 minus sin square theta t. So this is 1 minus sin square theta t is equal to eta 1 square into 1 minus sin square theta b parallel. Okay. Impress I can write sin square theta b parallel is equal to one minus mu 2 epsilon 1 by mu 1 epsilon 2 by 1 minus epsilon 1 by epsilon 2 whole square. Now, how did we get this equation? This equation we can derive by using the Snell's law. N1 sin theta I is equal to N2 sin theta t. Okay, where N1 is actually C into root over mu 1 epsilon 1 and N2 is C into root over mu 2 epsilon 2. If you substitute for sine values here, you will be able to derive this equation. Okay. Now, for non-magnetic medium, mu 1 is equal to mu 2 is equal to mu 0, implies sin square theta b is equal to 1 by 1 plus epsilon 1 by epsilon 2 or sin theta b is equal to square root of epsilon 2 by epsilon 1 plus epsilon 2. So, the sign of Brewster's angle for a non-magnetic medium is given by square root of permeability of the first medium divided by the sum of permeability of first and second medium. Okay. So, this is the Brewster's angle in which you will have total transmission. Okay. So, I will also give this as homework to derive this expression. Okay. So, we have covered although a small topic, but a large amount of portion. Okay. So, please go through this and let me know if you have any questions. Thank you.